In this optimization problem, we're going to be building a field, and it has a very particular layout. It's going to be rectangular, and it's going to be subdivided into 3 equal-sized smaller rectangles that are all going to lie parallel to each other, side by side. We've got 1,000 yards of fencing to work with, and we're asked to maximize the area that can be enclosed. So as always, the first thing I want us to do is draw a picture. And the picture isn't too bad. Just draw a big old rectangle. And, okay, subdivide it into 3 equal-sized side-by-side rectangles, like so. Once you have your picture, the next thing I always want you to do is label it. That is the way that you are going to be defining your variables both for yourself, so that you can come up with equations, and for me, so that I know what your variables mean. So let's call this entire side x, and this side y. That seems pretty reasonable. You can call it, say, width or length or whatever you prefer. Now we need equations. So what types of equations will we have, and will we have more than one? Well, we are working with, besides x and y, 2 other quantities here. Area, so we need an area equation, and we're given a length of fencing. So perimeter, although strictly speaking it's not perimeter. Perimeter would be the outside, and we've got a couple lengths going through the middle. But for lack of a better word, let's just say D for perimeter anyway. Okay, so our area is straightforward enough. It's the entire rectangle. It's just x times y. The fact that it's being passed through by these fencing pieces doesn't change anything. For the perimeter, well, let's add on to our picture a little bit. We know this side is also x, and then each of these parallel sides are y's. So we've got 2 x's and 4 y's. Notice that we actually ended up with 4 y's even though we are breaking it up into 3 pieces. I don't know if that's obvious to you when you picture it in your head. It's not quite to me until I actually have it drawn out, seeing that for 3 pieces you actually enclose it with 4 lengths. All right, and the last thing we need is 1,000. So that's my fencing length. So I'll set that equal to my p. So although I was worried about this variable p, we're not going to use it. Let me get rid of that right now. Right, that's always going to be equal to 1,000, so there's no need to always have to keep track of this p. So what do we do next? Let's be methodical here. We're going to identify what we need to do. We want to maximize area, right? That's exactly what we're told to do. So you want to maximize A. And therefore, that tells me it's this area equation that I want to be working with. And so we're going to take the other equation and use that to solve for and eliminate a variable. So let's solve our p equation. And yes, I did just erase p, but it is the second equation for x or for y. I don't care which, they will both work, and in this case, they're both going to be algebraically equally easy or hard. And then plug into A. All right, so let's take this equation, 2x plus 4y equals 1,000. I'm going to solve it for y. You may want to try solving it for x yourself, just so you can see the other way to do the problem. So 4y equals 1,000 minus 2x, divide by 4, gives me 250. 2 over 4 is a half x. Plug that into your area equation. Oh, and by the way, you may want to sort of just box this, not for me, but for you. So often in these problems, we come back at the very end, and we need to get both dimensions, for example. And this is exactly the equation you want to use for that. So you can make a little note of it so you can come back to it easily later. So plug that in for y in my area equation. A equals x, y. Like so. So there's your area equation, and really technically you're ready to take a derivative. I always like to simplify it if possible. The way it's written indicates we're going to do a product rule, but it's so easy to just multiply this out and make life easier later. 250x minus 1/2 x squared. That's my a of x. Okay. All right, so we're about ready to finish. We're going to take a prime, set it equal to 0, and that should end the problem. So a prime of x will be 250. We get a 2x times a half gives me just a minus x. All right, the 2 and the 1/2 cancel. So I got 250 minus x. That's about the easiest derivative we could hope to work with. Set it equal to 0. X equals 250 yards. As always, we go back, we reread the problem. What were we asked to find? Using 1,000 yards of fencing, what is the maximum enclosable area? Okay, so in this problem, I didn't read it when I was boxing my y. I thought I'd have to find dimensions. That's not what I was actually asked for. We want area. Area equals x times y, so you think, oh, I need y. Not really. We can go back to right here. Area equals 250 times 250 minus a half of 250. Well, 1/2 of 250 is 125. 250 minus 125 is 125. And you know what? You can leave your answer like this. I don't let you use a calculator, so this is just fine. The one thing I do want you to do is include units. It's going to be square yards, right? Because our linear lengths are in yards, and we're doing an area. And there we go.